precision-preserving yet fast object-sensitive pointer analysis with partial context sensitivity.
Thanks for the introduction. I'm going to talk about precision-preserving yet fast object-sensitive point analysis with partial context sensitivity. This is joint work with Jingling. Before presenting my own work, I want to introduce some basic concepts. Point analysis is the cornerstone of most static program analysis, such as tend analysis, type state analysis, and also static bug detections. Context sensitivity is important for a precise point analysis, and object sensitivity is arguably the best context abstraction for object-oriented programs. This has been repeatedly mentioned in related work in recent years. Despite this, it's still facing great challenges of efficiency. Conventional key-limiting object-sensitive point analysis is only scalable for some small values of k. Typically, k is smaller or equal than 2. 3 object-sensitive point analysis often fails to terminate in even 24 hours, while 1 and 2 usually finish in just a few minutes. Recently, it is increasingly noticed that blindly applying context sensitivity to all the methods in the program causes the exponential blow-up in the number of contexts handled. For this reason, a few efforts attempt to restrict context sensitivity to only some selected methods in the program. Such selection is made by a pre-analysis guided by heuristics or thresholds, and some of them can achieve better efficiency with a big loss of precision, and the others achieve high precision, but the speed up is not that impressive. The reason is that in one method, usually some pointers is sensitive to the context and some are not. In the general division, if it is classified context sensitive, it seems too conservative and loses the opportunity to further improve the efficiency. If classified insensitive, it seems too radical, so it may lose a lot of precision, and the loss of precision will in turn cause the redundant context and limit the speed. So here we present a radically different approach called EGO, which can apply context sensitivity to only some selected pointers. In other words, a method under our approach can be partially context sensitive. Furthermore, unlike previous heuristics or empirical ones, we can guarantee 100% precision theoretically. So next, I will offer you 3 main building blocks to understand how we achieve this. So firstly, the first one is the simple observation about how context sensitivity influences the precision. We take the identity function as an example. Identity function returns whatever it receives. In this example, it's invoked twice. Obviously, it has 2 entry flows under different contexts to P. It also has 2 exit flows from P under different contexts. If P is analyzed context sensitively, the 2 data flows go in parallel. However, if P is context insensitive, then the 2 entry flows get merged and P, and they cannot be distinguished when the exit flow is encountered. If we only have entry flows, we don't need context sensitivity for S, because the value of S will not affect any other pointers in the program. As for the pointer S itself, these 2 representations, the sensitive and the insensitive one, are actually effectively equivalent in terms of precision. Similarly, if we only have exit flows, we still don't need that, because though different objects are created and different call sites, they are abstracted using the same allocation sites. So it seems that the entry flows and exit flows are the necessary conditions for context sensitivity. Let's see the another example. It's still the former example, similar, but the distinguishment of the two newly created objects now become meaningful because of they have field access. For this one, actually, we still have entry flows, except that it's for R.F rather than R. So our condition of the context sensitivity of a pointer becomes the entry flow and the exit flow both exists for the pointer and any of its access paths. But the question is how to find it automatically. Our second observation is that the reachability formulation is necessary for such selection. Context-free language reachability has been used on point analysis for many years. Program is represented by a graph statically, and then point analysis is described with the production rules. One of its advantages is that it describes the point analysis precisely with basic items. And the field sensitivity and the context sensitivity can be described using separate languages. Unfortunately, all the past formulations, the safer reachability formulations for point analysis are for cosine sensitivity. Unlike cosine sensitivity, object sensitivity has never been described in reachability manner. The difficulty lies in the dynamic resolution of the context element. For example, for cosine sensitivity, the context element, the cosine, can be found statically, intuitively. However, the object sensitivity, under object sensitivity, the context element is the point to target of the receiver, which can only be found during the point analysis. To alleviate this, we established a new form of safer reachability. The part in the blue boxes is special for object sensitivity. For field access, the third and the fourth line, except for the conventional operation, base object is now regarded as a context transfer. For a virtual call, interprocedural data flows now has some field access features. Correspondingly, the production rules are also expanded. By doing so, this new formulation enables us to bypass unknown contexts of interprocedural data flows by connecting them with the receivers, and the automata will find the right target automatically. Besides, a field pointer now can be divided into two parts. The field is now regarded as a local variable and can join the reachability graph as a normal node. The base object is regarded as a part of the context of this variable, so should be pushed into the context stack. Now let's back to the former example. We still only have the exit flows, but we have field access. Now, according to the language, the store operation will enforce the inverse traversal along the exit flows. Now we can precisely define the context sensitivity for each pointer. But unfortunately, this process is undecidable because it relies on the intersection of two context-free languages, and according to the theory of computation, this is an undecidable problem. A computable analysis can be obtained by regularizing one of them. Simplifying LC is unacceptable because the context information is exactly what we want. So we have to simplify the LF. There are many ways to do so. This is our regularization of LF. It eliminates the field matching by equivalently modeling the load and design, but store operation is still kept, so it is more precise than a one-limit access path. This language actually keeps as much information as possible without introducing much complexity. And then the selection process can be finished in polynomial time. Of course, by doing so, we introduce some false positives. Then what's the over-approximation? For the last example, suppose the second field F is changed to G. Then the simplified language cannot distinguish the F and G, so the selection result should be exactly the same. But the actual fact is that the two data flows go in parallel, even R is context insensitive. So this is an overclaim. Now we have a polynomial selection process, but this is not enough. Polynomial is still a little bit heavy for a preanalysis. We found that as a preanalysis, we do not need to calculate the 4 points to results. What we only care about is whether is the existence of the entry and the exit flows. So what if we don't keep the long context string, but only whether context sensitive or not? Obviously, simply doing so will cause an unmatched problem. The entry flow under context A will falsely flow out under context B. Another key observation here is that under object sensitivity, context transfer always happens at the allocation sites, the green one. So the path between two objects is always regular. Which means its behaviors under different contexts should be identical, because this is the definition of the regular language. This enables us to summarize these paths and avoid matching process for different contexts. And this ensures each node is visited at most once, hence the process can be finished in linear time. The selection algorithm can be eventually written in several simple propagation rules. To evaluate our approach, we use 12 large popular Java programs. And the result shows that the points to relation is identical to the original, and the time consuming is only a fraction of the original. This is our selection result. The context sensitivity distribution in terms of method compared with the prior art. We can see clearly that some sensitive and insensitive insensitive method now become partially context sensitive. If we look at the context sensitive distribution in terms of pointers, we can see actually our division is much more powerful, because we can identify more context insensitive pointers. That's why we're faster. To conclude, we present EAGLE, a new points to analysis technique, which enables partial context sensitivity. The selection lies in the new form of self-reachability, which equivalently models field access and method invocation to some extent. The selection is implemented as a fast pre-analysis, which is linear to the size of the graph. And finally, we have evaluated our approach, and we get 100% precision with a remarkable speed up. Thank you.
We have time for a few questions while the next speaker sets up.
Two questions. So what have you implemented this in? Is it in Datalog or?
Excuse me?
In which language or framework did you implement the work? Is it in Dupe or Datalog or some other thing?
Java.
It's in Java.
So pure Java, yeah.
Did you use Suite or something then? Or?
Yes, it's on top of Suite.
Oh, okay. And the second one, so you are in the example which you had shown for motivating different exit flows, you did not have heap cloning as such. So, I mean that the object allocation site you mentioned was the same in different contexts, and hence it's not contributing to different.
Actually, it has.
Okay.
So that's why we changed the example. Changed the example.
Okay, so you do you have
We have
added
heap cloning.
Okay.
Yeah.
Okay. Thanks.
All right. One quick question. Big.
Oh, hi. Can we apply eagle to other contexts, for example, call size sensitivity?
Yes, but according to our investigation, we think eagle cannot ensure the precision, 100% precision for call size sensitivity. But the result is, I think, effectively just similar to this one.
Thank you.
All right.
Thank you.